I'm Daniela, and I'm standing in for Liz just for a few minutes. She's running a bit late, but we thought we'll start the workshop because we want to make the most of it. So thank you for coming, and we're going to hear from Professor Zoltan Diaz. There's Liz. And this is a workshop about principles of Bayes factors. So yeah, and Joe, I'm going to pass the word to Professor Diaz.
Thank you. So what I'd like to do, first off, is to put Bayes factors in context. So you understand the problem, I use them to solve, principles for using them, and also criticisms of Bayes factors, which I think, to understand the criticisms of Bayes factors, will help you use them appropriately. Because as I'll say, I don't think there are any criticisms of Bayes factors, there are only criticisms of misusing them. So this morning will be about putting things in context, and this afternoon we'll just do lots of practical stuff, so hopefully you brought with you, don't have to bring your data, but just your know something about your experiment, some issue you might want to be solved with a Bayes factor. So this is what I'll do. Talk about the problems to be solved, and the other solutions that are on the market that you might be tempted to use, and I'll say something about why I don't think they work generally, what a Bayes factor is, and then some principles for using Bayes factors, which I sort of put together because I want to write a paper as a sort of consensus statement amongst psychologists or statisticians who use Bayes factors as principles they could agree on for using Bayes factors. And then I'll deal with the criticisms. So to put things in the broadest perspective to begin with, we're going to ask what are inferential statistics for. So inferential statistics are the statistics when you're trying to generalize from a sample to a population. And generally you can divide that endeavour into two, depending on the question you're asking. You could be asking the question, how much or how many? And that's an estimation question. Or you could be asking an existential question, which is, does something exist at all? So if you wanted to know, for example, what proportion of Americans would vote for Trump now, that's an estimation question, right? How strong is the relation between exercise and heart rate? That's an estimation question. But you might also ask the question, is there a relation? And then that's the existential question that's answered by hypothesis testing. Now, some problems you might be faced with as a user of inferential statistics might be more one way or the other, or involve both. Voting behaviour and other questions about people and animals in the wild, as it were, sometimes are more about estimation than whether something exists. I mean, if you take it for granted that the relationship exists, that there are some people who will vote for Trump, that's not the issue. The question is what proportion of them. Indeed, if you're dealing with issues in ecology or correlations between different variables where you haven't causally manipulated anything, the question of whether there is a relationship isn't one that's seriously in doubt, and then that becomes an estimation question. Now, common view, and my view, and what I take to sort of be a sensible view, is we want to answer both sorts of questions in general. So given doubt about something's existence, an interesting level of doubt, we want to know evidence for whether it exists, the existential question, and given that something credibly exists, to estimate how big it is. So we want to do both things. But there is a counter view. And that counter view you find both on the Bayesian side of the sort of inferential statistics divide and on the orthodox view. And that's, we'll only want to answer one sort of question, which is how much. All we should be doing is estimating. For example, Jeff Cumming pushes this view in what he calls the new statistics. Or on the Bayesian side, you have people like John Prushke or Gelvin. Now, one reason why I think they have that view, or you might have a view like that, is because there's a sense that we're in trouble. There's a credibility crisis, a replicability crisis, and one culprit the finger points at is significance testing. So, significance testing is hypothesis. It's a version of hypothesis testing. It's answering the existential question. So, maybe if we only estimated, we would solve some of our problems. Well, let's look at some of the questions we might ask that are, on the face of it, hypothesis testing questions. Like, was there any conscious perception of the stimulus? Interest in subliminal perception is a question you need to ask. You're asking an existential question. Do people perform above baseline? If interested in learning, like I take a lot of you are, then that's probably a question you often ask and indeed come to conclusions about in the discussion section of your paper. You answer an existential question. Children did learn this task, or whatever the case may be. Was the evoked potential higher for this sort of stimulus or that sort of stimulus, and so on. So as experimentalists, psychologists, linguists, we certainly often pose existential questions, hypothesis testing questions. So you might ask, could we get away with an estimate rather than a hypothesis test in those cases? Because this seems to be what some very clever statisticians are telling us to do. And indeed, that's sort of one of the solutions on the table for dealing with the credibility crisis and dealing with some of the issues I'm going to use Bayes factors for, so I just want to consider it. Just to take a question as an example question, do people perform above chance? Do they perform above baseline? If you're doing estimation with sort of ordinary statistics, you do this with a confidence interval, which is an interval, lower limit or high limit, and you say, we accept all the values within this interval as possible population values, and we reject everything outside of it. We make this decision. We reject everything outside the limit and accept everything within it. And if we do that, then a certain proportion of the times we'll include the true population value. Bayes, you can do something very similar, sort of a confidence interval, you have a credibility interval, and in the Bayes case you get a probability density distribution of possible population values, and then the area under the curve is the probability that the true population value lies between those limits. It's an area under the curve. See, that area there is the probability that the true population value lies between here and here. So, I just want to ask you to think about one thing now while we're on that. It's the area under the curve, in other words, the shaded area here, for the probability that the true population value lies between here and here. So what is the probability of a point value? Like the probability that it's exactly, the true population value is exactly 51% or exactly 50%. Well, the probability that it's exactly any value is has zero area under the curve. So the probability is zero. I just want you to bear that in mind. From the Bayesian estimation point of view, the probability of any particular value is always zero if you have one of these continuous probability distributions. Okay, so we have a question, do people perform above chance? Let's say chance is 50%. Let's say you calculate a 95% confidence interval, and it goes from 45% to 55%. Notice that that includes the chance value of 50%. Now, sort of as an aside, in terms of significance testing, what would be the result of the significance test here? Would it be significant or non-significant? It would be non-significant. That's what it means when your confidence interval includes the null value. The test is not significant. Now, so the confidence interval goes from 45% to 55%. Remember what that means. The confidence interval means we accept all the values within the interval as possible population value. values. So can we conclude that people performed at chance, that the population value is 50%? That's what a lot of people do conclude from that, because it's a non-significant result. And they might even phrase it in terms of confidence interval and say the null hypothesis value is within the confidence interval. We can't reject it. But there's a whole bunch of things you can't reject. We can't reject, yes, we can't reject 50% chance. We can't reject 51%. We can't reject 54%. There's a whole bunch of values we can't reject. So we can't conclude that people were performing at chance, based on the confidence interval. Chance is possible, but so is a bunch of values of people are performing better than chance. Now, from it doesn't really, the conclusion doesn't in substance change if this was a credibility interval rather than a confidence interval. In fact, as I was getting at before, with the Bayesian credibility interval, chance always has zero probability of being the right value because chance is a point value. So you can never accept chance using Bayesian estimation. You can never accept a point value. So we can't conclude that people performed at chance. In other words, we can't get evidence for the null hypothesis if we're interested in a point null hypothesis by using estimation procedures, whether Bayesian or otherwise. So what could be a solution? By the way, feel free to ask questions. So if anything I said isn't clear, then feel free to interrupt and ask me. So the conclusion so far is, if you're interested in point null hypothesis, like are people performing at 50% chance or not, you don't have grounds for accepting that if all you do is estimation. So what could be the solution? Well, one solution is we say, well, we're not really interested in a point null, in just 50%, because surely there's a range of values, although not quite 50%, are so small as to be meaningless. So what about if we came up not with a point null, but with a null region, where we say everything within this region is too small to be theoretically meaningful or practically of any interest? Well, to do that, what we need to do is to come up, well, we have to define the region. And to define that region, we need to define what is the minimal interesting effect size. So you might say, well, 51%. If people were less than 51% correct, that's so trivially small that for all intents and purposes, there's no interesting level of learning going on here. Or no interesting level of conscious perception or whatever it is. But somehow we have to decide on this minimal interesting effect size. And given that we do, we then have a region. And then this changes the way our inferences can work. So I called it inference by intervals, because now we have an interval, or a region, instead of a point. And some set of decision rules or inferential procedures were described, which is similar to the ones I'm about to describe, in 1983 from a Bayesian point of view by Friedman and Spiegelhalter. So how could it work? Let's say you defined a null region and then you come up with a confidence interval or a credibility interval and you find that it lies completely within the region. Well, now it seems we can come to a conclusion, unlike what I said about the point null, because then from a confidence interval point of view, for example, all of the values that we accept as possible are boringly small values. Values that we've pre-decided are too small to be support for our theory or practical intervention or whatever it is. So if the confidence or credibility interval lies within the null region, we can accept the null region hypothesis, to put it in orthodox terms. So say And then if the interval lies outside the region, we can reject the null region hypothesis, because all the values we regard as possible, or probable from a Bayesian point of view, are, we've decided, interestingly, large values from the point of view of theory or practical intervention. And if our interval spanned both null region and theoretically interesting values, we'd have to say, well, it could be one and it could be the other. We need more data if we want to be definitive about it. Well, this was the first proposal of this that I've seen, I say, is 1983, and around about the same year or just afterwards, from a frequentist point of view, very similar reasoning was put forward under the name of equivalence testing. And a sort of recent proponent of that would be Daniela. Now I see the sort of the logic of that, and I accept it as a possible way of thinking. But I want to give you two problems why I found in practice it not to be generally useful. And in fact, problems were foreshadowed in the original paper by Friedman and Spiegelhalter. They looked at surgical intervention, and they interviewed a bunch of surgeons to try and find what this minimal interesting value could be. And they said that the estimates of this value that they got from different surgeons were so variable, they couldn't see a way of meaningfully implementing the procedure because it depended on something about which there was very little agreement amongst the experts. That's not to say it'll always be that way, but they found in the particular case and in the paper proposing the method that there might be problems here. So, the first problem is you need to specify minimally interesting effect size in a non-arbitrary way. You see, if it was purely arbitrary just because you reached inside your soul and came up with an answer, then your conclusions would also be arbitrary because the conclusions depend crucially on where you put that boundary. Now, there might be some ways of approaching this. For example, in the case of depression, some committee has decided that 3 units on the Hamilton depression inventory is a clinically meaningful change. But even if some committee has decided that, you can still ask, did they have good reason to decide that? Otherwise, a committee is something like a black box. Well, let's take a case claiming stimulus is subliminal. We need to have some measure of conscious perception, which for some people consists of people's ability to discriminate whether the stimulus was there or not. Well, then we need to decide, if we're going to use this method, what's the minimal level of discrimination that will be sufficient to say there's a good enough level of conscious perception there to say people did consciously perceive it. It's a difficult question to answer. Well, one way you could get at this question is to look at levels of performance effect sizes in the literature that people have accepted as being meaningful in the past. So in this particular case, a PhD student of mine, Anne-Marie Armstrong, found 52% performance was discriminating degraded stimuli, and we concluded that by this sort of measure of conscious perception, objective measures, people were above the threshold of conscious perception. The reviewers didn't disagree with us, and since publication no one has complained about this bit as being too small to be meaningful. So it sort of looks like something that could be accepted.
So,
yeah.
But where did the 52 come from? How is that?
So that was a level of, we asked, this is subject's performance in this experiment. Yeah. They had this discrimination performance, it was reliable, and we concluded that people could discriminate. And this demonstrated by this, if you accept this sort of measure, which we in fact didn't, but anyway, if you do accept it, that this shows conscious perception.
Oh, sorry, what I'm not clear about is 52% was the score that they got on the task.
Yes.
And then what was it you used to say, or was it just arbitrary that you decided that was?
So now we didn't use this method there. Okay. So what I'm doing is I'm saying, how could you come up with a minimal interesting effect size? We could look at past literature where people had performed above chance and people had accepted that as a meaningful amount of performance. So this is just a case where people performed above chance. We concluded people performed above chance. And so No one disputed us with that anyway. So is that a meaningful level of performance on this task for establishing conscious perception? So maybe there are ways of getting minimum. This doesn't quite nail the issue, of course, because you could dispute that we shouldn't have accepted it. But also it just sort of sets an upper limit. Because what if we got 51% and nobody disputed us? Where do we actually put that minimal interest in effect size? Actually, we want a good reason for it. But let's say we accept 52% is interesting. So we go, well, how about 51%? Maybe that's a minimal interest in effect size. Okay, well, let's go with that. So 52% is good enough. We'll go with 51% as being too small. So that would set a null region as 49% to 51%. Now that brings me to my next objection, that if you come up with some meaningful null region, you're going to need a ton of subjects to squeeze a confidence interval into that tiny region, what will normally be quite a tiny region. So I looked at a past paper of subliminal perception factor, classic one, by Stanislas-Dehaene's group, where he claimed stimuli were subliminal. In fact, he got a discrimination of 52.9%. It was non-significant, but already bigger than the one that we'd concluded showed above chance performance. But what I took from this was the standard error that he had there. He had 27 subjects. Now you can work out, given that, how many more subjects would he need to shrink the confidence interval into such a tiny interval, and you'd need about 400 subjects. Now, I don't know if that strikes you as reasonable, but what I'll be able to argue later is that's way too many, in the sense is you can get evidence on rational grounds for a null hypothesis with considerably fewer subjects than that. So problems with inference by intervals. And I've gone through this because it is out there as a Bayesian way of thinking as well as a non-Bayesian frequentist way of thinking. So this is my reaction to it. Is first of all, you need to specify minimally interesting effect size in a non-arbitrary way. And I have thought about hundreds of cases that, within experimental psychology papers, because I've given master students the task of thinking about this, and then I thought about their answers. And I just found it extremely difficult, in all those cases I thought about, to come up with a non-arbitrary way of saying what that null region should be. I couldn't point to a number and say it's that number there for this objective reason. And then when you do come up something that seems reasonable, you need way more subjects to come to a conclusion than in fact is reasonable. In fact, I personally don't know of any case within experimental psychology where people have used this a system of inference by intervals or equivalence testing to conclude that the null hypothesis is true. If you know of any case, let me know, but I know people who promote it, but no actual practical use of it. And probably for the reasons that I've talked about. So the moral I take from this is the attempt to smuggle in hypothesis testing to estimation does not provide a general solution. I see the logic of that approach, but I don't see it as one. So in other words, the Gelman way of doing Bayesian statistics, the Pushki way of doing Bayesian statistics, I don't see as a general solution to the sorts of problems I'm confronted with in every paper that I write, which needs a hypothesis testing type of answer, because I'm asking an existential type question. I want to know, do people fall above chance? Is there an interaction here? And so on. Okay, so if estimation isn't the general solution, and by the way, I'm not saying don't do estimation, we always need to estimate. It's just that we also need to ask other questions, like hypothesis testing questions. You can say, well, what's wrong with significance testing? And my general answer to that is, when we set up a null hypothesis and an alternative hypothesis, collect some data, typically we want to be in a position where we can say, did we get evidence for H0, evidence for H1, or no evidence to speak of? There's 3 evidential states of affairs we can be interested in. And p-values, to the extent they make an evidential distinction, only make a 2-way one. This box versus that box. and don't make any distinction within the box. So p-values, and I've argued elsewhere, even if you put in power, don't allow you to distinguish evidence for H0 versus no evidence at all. You need more data. So we need something else. I just want to take a slight digression here for you to think about, because I think there is something to take home from those people pushing estimation. I mentioned Jeff Cummings, Gelman. That is, maybe we don't need to do hypothesis testing as much as we habitually do. In particular, if there's no doubt that something exists, then just estimate. For example, correlation between two measures of the same thing, performance and tasks that obviously people will learn. And I guess I first really thought about this only, or really came home to me only a few months ago when we're writing up a paper, and I was thinking about how to do a Bayes factor for each of the tests in there, because I have a policy of a B for every P, a Bayes factor in every case. I would calculate the significance test. And my sort of struggle to come up with one which I thought was actually appropriate led me to realise the problem was this wasn't the case where hypothesis testing really added anything. So this was, in fact, a norming study. We were norming a test of hypnotic responsiveness, and we had things like different measures of hypnotic response. But really, there's no question that these things would correlate and correlate to a high degree. If all we did was estimation in this paper, it would read perfectly fine, and there would be nothing in the discussion we couldn't talk about. So we went over to the whole paper being one that just had credibility intervals and estimation. So I'd urge you to think about that. Is this really a case of where you need hypothesis testing? I would just say if you do estimate, say things like if it's credibility interval, performance is probably between 45% and 65%. Don't slip into then doing hypothesis testing and saying therefore people are at chance or something like that. If you estimate, just estimate. And also don't bother saying the opposite, therefore people are above chance. Okay. Confidence interval excludes chance value. Because then you're hypothesis testing again, and you want to think about the ideal way of hypothesis testing, which I argue isn't significance testing. So, in summary, estimation does not allow us to get evidence for no effect. Significance testing doesn't either, so we need something else, which is, of course, the Bayes factor. So that was sort of to put in perspective, if you're interested in Bayes, certain Bayesians you'll come across. For example, if you pick up Gelman's book, Cauchy books, people in that tradition, you'll get an answer to how to be a Bayesian that would be very different to if you approach people who are into Bayes factors. And that's because one group are into estimation and another group is telling you how to do hypothesis testing. Yeah.
I don't know if you're going to mention this later, but in case it fits now, I wonder if you could just say a couple of sentences about why going from 90% power isn't a solution to, why that isn't a good way of getting, of not having a problem with type 2 errors.
Right. So why doesn't power solve?
Why doesn't power solve the problem? Yeah.
So why doesn't power solve the problem we're interested in? Power doesn't solve the problem because let's say you've got a null hypothesis of no effect. A past study shows an effect of a certain size. You have an estimate of the effect that you're interested in. So we have an effect here for the null value. We have the effect here that we've used to calculate our power on the basis of. And in fact, we make sure we have 95% power to pick up this effect that's estimated from the past study. So. And then in our actual experiment, the effect size we get is bang in the middle of the two. Now, so the first point I want you to realise is you can have 95% power and get an effect that's exactly halfway between the effect size you use for power estimate and the null null value of, say, 0. Now, if your data mean, effect size, lies exactly halfway between this model, the null model, and this model, H1, can it provide you evidence for either of them, for one more than the other? So I hope what's intuitively obvious is no, it can't be evidence for one more than the other because the situation is symmetric. So how can one be favoured more than the other? It's bang in the middle of the two. So you can have a high-powered, non-significant result that is not in any way evidential. So high power does not guarantee, a high-powered non-significant result does not guarantee you have evidence for the null hypothesis. So, and that's the problem with power. It doesn't give you a measurement of evidence. So if you're interested in whether you have evidence for H0 versus H1, well, while often a high-powered study will give you good evidence, it's not in any way guaranteed. So if you want to know that you have evidence for H0 versus H1, we better use a measure of evidence that will tell us whether in this particular case we have such evidence or not. I have a paper about that on my website, and there's a talk on my website about that as well, if you want to go into more detail. 4 reasons to be Bayesian. Look at the paper or the talk. And sort of to follow on from that, one thing we could do is start from first principles with what would be a measure of evidence, and then use that. And so that's what the Bayes factor does. So let's start with the axioms of probability, and what we'll assume is that strength of belief should normatively follow the axioms of probability. That belief is the sort of thing that should follow the axioms of probability in some idealized world. So I'm not saying belief does, but just that it should. So imagine you had a degree of belief, a strength of belief, or degree of plausibility in H1, or strength of belief in H0, before you see some data. So this term here is your prior confidence in H1 rather than H0. Your prior odds in favour before you collect some data. And over here is your probability, strength of belief you have in H1 given the data you just collected. So it's what you call your posterior odds in favour of H1 versus H0. Now this is just a couple of steps in rearranging the axioms of probability, and what they tell you is, having collected some data, the amount by which you should update your prior odds to get your new confidence is exactly this thing here. It's how well the data are predicted by one model versus the other. And that's what we call the Bayes factor. Now, given you think the axioms of probability are, as I say, normative model of strength of belief, then what this is telling you is the Bayes factor is the complete description of everything that's needed, you need to know to change your strength of belief. There's nothing left out, and it includes everything that should be in there. So let's define strength of evidence as the amount by which you should change your opinion. Then the Bayes factor is, from first principles, the measure of strength of evidence your data provide for H1 versus H0. So if the Bayes factor is about 1, that means you shouldn't change your opinion at all. Well, that means the experiment wasn't sensitive in discriminating H1 from H0. And the way you can put it either way around, it just sort of depends which term is on the top and which is on the bottom. The way around I programmed it on my calculator is the Bayes factor is more than 1, then you should shift your opinion more towards H1 than H0, so it's evidence for H1 versus H0. If the Bayes factor is less than 1, the data support the null hypothesis rather than the alternative. Now, strictly from basic point of view, all you have is this continuous measure of strength of evidence, but it would be nice to put some sort of conventional labels there for thinking about the amount of evidence that we're dealing with. And Jeffries, who in his 1939 book, Theory of Probability, virtually single-handedly laid out a complete system of inference based on base factors, suggested 3 as a useful benchmark because it found that it corresponded to Fisher's use of 5% significance, in the sense that when Fisher said this was significant at the 5% level, Jeffries would find he'd get a base factor around about 3 or more. That's something that's not at all guaranteed, by the way. It's just something that will arise if you get in your data an effect size that's similar to the sort of effect size that you expected. Then this turns out to be approximately true. So Jeffries called this substantial evidence. Maybe one way of thinking about what he meant, or what we should mean by that, is sort of worth taking note of. Base factor 3 or more is worth taking note of. Perhaps worth exploring further. Not definitive, but might be something going on here. Now, once we have a threshold of 3 for noticeable support for H1 over H0 by symmetry, we also have, to an exactly equivalent way, a measure of evidence for H0, base factor less than a third. Now, one argument is whether we should use a measure of evidence like this, and see, I think we should, and it's useful. But a separate argument then becomes what should be good cutoffs, what would be useful cutoffs for the scientific community to use. I've been using 3 because then that means my conclusions line up with 5% significance value. So I give a big B for every P, and so I'll say, F equals P equals so-and-so, effect size, B equals whatever it is, all in that sort of little line that you have for the results of a given effect. And then I interpret the results with respect to the B. So I'll say there was evidence for a main effect here. And a significance tester going through that would in most cases, agree with what I was saying. And say, well, it's significant, and he's claiming that there's evidence for an effect. Yeah, I agree with that. I'll just be saying some other things that the significance tester might find slightly odd, but wouldn't disagree with, per se. For example, I might say there was evidence for there being no interaction. And you would say, well, it was non-significant, I guess that's one way of putting it. But I'll be making a distinction there, because sometimes I'll be saying, and there was no evidence one way or the other for whether there was an interaction. It would be non-significant. So I'll end up making distinctions that the significance tester is not in a position to make. When 3 1/3 are my cutoff there, so 3, I get disagreeing with the 5%. But there is a debate to be had where that 5% significance, and hence also base factor 3, is really what we should be using, or if that isn't a little bit on the just noticeable different side of things. So, for example, Cortex will be going over in registered reports to a significance of 2% and a base factor of 6. And some journals are thinking about a base factor of 10 being the cutoff. Or you could have 0.005 for significance and a base factor of 20, and an article is about to come out arguing for that. So I think that's an interesting discussion to be had. So let's just, yes.
Sorry, it's maybe a stupid question. But in a similar way, if 3 matches up to 5% roughly, when you have things like the Bonferroni fraction where you would have multiple tests and you adjust the p-value, would you do a similar thing for phase?
I would not, no.
Okay.
Yeah. So you don't adjust...
It's not like you make it 6 if you have multiple tests. That doesn't make sense.
No, that's right.
Okay.
Because, so the issue is when you have multiple tests, if you're into error correction, then the more tests you do, obviously the more errors you can make. But error correction is one thing, and evidence is another thing. So the evidence, these data for that hypothesis remains the same, no matter what other tests you're doing. But my sort of general answer to that is, if you're thinking about correction, that's probably, is that because in some sense these tests are addressing the same theory? And then what you need to do is to consider all the data that address that theory to know the evidence for that theory. So a bunch of non-significant results would in fact may well in fact count against the theory. Now, notice what we have here is, when we use base factors, this is a symmetrical state of affairs that we didn't have with p-values. Namely, we have evidence for H0 as much as evidence for H1, whereas in p-values that was asymmetric. People had a sense that they could reject H0 on sort of a firmer footing than they could accept it when you're doing significance testing. And so what that means is if you're trying to get a paper published, you're kind of pushed towards wanting to get significant results rather than non-significant results. At least that was the general pressure. And that has led to a number of problems, like the file draw problem. When a key result is non-significant, people don't publish it, at least historically. I believe that has been the case. And so you end up with published literature that's highly biased. If you did a meta-analysis or something on it, you would get a distorted view of the amount of evidence for there being a certain sort of effect. But there's also been something equally problematic in the other direction, which is when people did get a key result significant, they irrationally then had the other tendency, which is to treat any non-significant result as having evidential value. So let's say the main effect is significant, you then would hear or read people say, or hear in a talk, people say, but it didn't interact with gender, so therefore we forget about gender. Because there was a non-significant interaction, you see. So it's easy to show that there is a widespread bias that when the paper is published, because it had a key significant result somewhere, people who use non-significance willy-nilly to assert the null hypothesis. So what you could have, for example, is a drug is effective in some way, so lowering blood pressure, treating depression, significant result, and then the drug company claiming, and there was not these side effects because they were non-significant. It doesn't increase the rate of suicide in teenagers because it was non-significant. So this can be life or death. It's not just groundless. We've been using groundless techniques for developing theory, which is worrying enough. It also has practical implications. So that was p-values though, but with a base factor, which is symmetric, we get around some of these problems, if not completely, at least to some extent. It should help against publication bias, because we now have evidence in favour of the null hypothesis, which is just as good in an evidential sense as evidence for H1. So that should make the publication record less biased. And conversely, it will help people only draw conclusions about the null hypothesis when they have evidence for the null hypothesis. So just because something is non-significant doesn't mean you have evidence for the null hypothesis. The people have been going around assuming in every paper or reading every talk I go to that it does. So it will correct the problems that go in both directions there. It also, and one way of thinking about it, this comes from the symmetry, is we can collect data until we have enough evidence. So there can be optional stopping with base factors in a way that is forbidden with p-values. So I'd like to say that base factors will address some of the problems we've been having that produce the credibility crisis. But I also want to say that it's by a long shot not the complete answer. And there's many other things we should be doing. And Chris Chambers' new book, The 7 Deadly Sins of Psychology, I think is an excellent and highly motivating read about different solutions that are on the table, including pre-registration that I know some of you are already doing. So what we need to have a base factor is we need to know how well we can predict the data from each of the hypotheses, H0 and H1. And in order to do that, we need, in essence, three models. A model of H naught, and I'm calling the model of H naught. In other words, we need to know what does H naught predict in order to know how well it predicts the data. And, well, we know what H naught predicts. H naught says that the population mean difference is exactly 0, or the population slope is exactly 0. And this is just a fancy way of describing that. We've plotted here different possible population values, population differences in means. This is their plausibility on H naught, and H naught is just a spike on 0. So there's only one population mean difference that's plausible given this model, and that's 0. Or 50% or whatever it is, but that's sort of, think of it as 0, it's too easy to convert to 0. And to know what we're predicting, we also need a model of the data, which is to say something like, are my data normally distributed? It's the same sort of question you would ask if you're doing a t-test or something like, is this a binomial situation, is it a normal distribution, and so on. In other words, in order to predict our data, we need to know not just what the population value is, but how much and in what way our data are going to scatter around that population value. So, so far, this is just what you do if you're doing a t-test or a binomial test or any other than normal tests that we're used to. This is the same, as it were. But what we also need to do a base factor, which is a different thing, is we need the model of H1. In other words, we need to know what does our theory predict, what does the alternative hypothesis predict. In particular, we need to know what is the plausibility of different effect sizes given our theory. Are any values ruled out? Are some values more likely than another? And so on. And this is what we haven't had to think about in order to get out a p-value. P-values you get out just with these two models. But if we want a measure of evidence, we need to know how well are the data predicted from H1. And I just want to motivate the thought that we do need this because this model of H1, because this is precisely where base factors differ from, say, t-values or binomial tests and so on. And so it's where, if you're going to criticize base factors, you criticize them, or if you're going to criticize a particular base factor, you would criticize them. Or if you were just thinking about, from a practical point of view, do I really want to go ahead and do this? This sounds too difficult. This is the bit which you're going to find difficult because it's the bit that's new compared to what you've been used to. So I just want to motivate that, of course, it's needed. Okay, so there's no question about it being needed. If I ask the question, is there an animal in the room, unobscured by people? So this is an existential question, a hypothesis testing question. And you might want to draw the conclusion there's no animal here, which, in other words, the null value of no animal. That depends on my model of H1. So, in other words, what size animal could there be there if there were one? And if I said, well, the animal that could be there is this elephant, unobscured by people, all you have to do is look at that picture and say there's good evidence that there is no animal there, given the sort of animal that could be there is this elephant. But if I say the animal that could be there is this tiny little cat, and you look at that, you'd say, well, the evidence isn't clear. Okay. In fact, I had to look at this picture because I wanted to use it for about half an hour before I found the cat. And sort of looking for something tiny, given the noise that's there, is obviously very difficult. And what it means in an experimental point of view is you increase the number of subjects, which is like what I did on my computer screen, is to blow up the image so I could see more and more closely, despite my failing eyesight. And I did eventually find it. It was in there. It was a little bit of a cheat. Well, it is the cat anyway. So, and that's making your standard error smaller, is equivalent to blowing up the image until you can see more clearly. But clearly, evidence for something not being there depends on a model of what could be there. That's the moral. And whether Bayesian or otherwise, saying there is no signal depends on how big a signal we could expect relative to the noise. So we must have a model of H1 to get evidence for point null, is really the point I hope you intuitively feel. You can't just say there was no effect there, evidence for no effect there, if you have no idea what size the effect would be. So the moral is we do need a model of H1. And what I hope that is just intuitive. It doesn't matter if you're Bayesian or non-Bayesian or whatever you are, unless you know what is the size of the thing you're trying to pick up. And there's, you see all this noise there. You can't draw any conclusions at all until you know what it is, what size effect is you're trying to pick up. So we need a model of H1. So how do we model the predictions of H1? Well, H1 is really just a model of our theory. So how do we derive predictions from theory? Well, we use assumptions, and we want those assumptions to be scientifically informed and otherwise simple. And that is really how we proceed. And it's as straightforward as that. So I hope that just sort of seems trivially true, and that's really just the basis from which we'll be operating from now on. I'll be asking you to think about whether the model of H1, what is often called the prior, is, in your scientific judgment, a good representation of the theory because it's scientifically informed and otherwise simple. And just to go through a little example, and then I think we'll have a break for 5-10 minutes, just so I haven't been tied out listening to me for an hour. So imagine there's a study, in fact, I've taken this is a real study. People meditated on breathing for every day for 2 weeks, at least they're meant to do that. And it increased self-rated mindfulness by 0.6 of a point. I looked at the scale they used, the mindfulness scale, the FFMQ, was a 1 to 5 scale, which goes from something like, you ask the questions, how often do you do various things, from hardly ever to almost always. Okay, so fairly typical sort of Likert scale. And you think, well, that's interesting, just 2 weeks can increase mindfulness with this intervention. Mindfulness is meant to be great stuff. Is there other sorts of interventions that might work just because sitting down and concentrating on your breathing maybe doesn't work for everyone? There might be different things more suitable for different sorts of people. The other thing people meditate on traditionally and in these sorts of more extended interventions is movement like walking. So why don't we just do the same study and we'll get people to meditate on walking instead of breathing and keep everything the same. So this is not a trick question, just a sort of a genuine question. Not really knowing anything else, or without there being anything else that's particularly relevant other than knowing what I've told you. What size effect would you expect in the follow-up on the same scale and everything else the same? Probably about 0.6 units. Yeah, the same, exactly. The same, yeah. It at least, you might think it's not necessarily going to be exactly the same, but it's a good measure of the order of effect we're expecting. It's something like that. Okay. So I just want you to consider 2 further facts, which I often draw on, because what we need for the base factor to reflect what we actually think as scientists is what we actually think as scientists is not that one value is absolutely the value we expect. We think, well, it's roughly in the neighbourhood of what we expect, but bigger values, smaller values, they're all quite possible. Okay? So what we need to do is to get some idea of what range of values are possible. Some values are more likely than others, to reflect what we genuinely think as scientists, because the point estimate doesn't capture what we think as scientists typically in a given situation. We think there's a range that's not possible and plausible. So one factor to bear in mind is the reproducibility project of Brian Nosek from a few years back, where they tried to directly replicate as directly as possible 100 studies from psychology in prestige journals. And what I want you to think about from that particular set of results is the effect sizes they obtain. So if you plot the effect size here from the original research, and then what they got in the replication, this line here is the line of identity. So if the replicated effect sizes were more or less what the original studies had estimated, you would expect a scatter of lines along that line of identity. This line here is 0 effect size, and what you find is a scatter of points between 0 and the original. So in general, effect sizes were smaller than the original ones. And this is another set of replication attempts of a similar nature in behavioural economics, slightly smaller scale. They're plotted a bit differently. This is 0 effect size. 1 has been scaled to mean the original effect size. And what you get is something extremely similar, where the replications fall between 0 and the original, more or less. Sometimes a wee bit more, but they're more likely to be smaller than bigger. Now, there's all sorts of reasons why that could be true, including publication bias. But I reckon that qualitatively similar finding would be true even if the original study is your own study and you never published it. Because why did it catch your eye and make you think, ooh, that would be a good one to follow up on? Well, those effects that you've estimated as being higher than the true effects are more likely to catch your eye and say, ooh, that would be a great one to replicate. So probably just dealing with our bias as researchers, the conclusion that smaller effects are more likely than bigger ones will apply even to your own unpublished research that's caught your eye and you want to follow up on. So that's one point. And now the next point I want you to consider first sounds a little bit more arbitrary in a way. Fortunately, it turns out to matter less, which I'll come to, but it'll be useful to think about in the first instance, even though I'm going to sort of, as it were, completely relax this assumption later. Now, this study by Kuberg at University of Salzburg was a meta-analysis of all sorts of domains within psychology. And the modal effect size they got was a Cohen's d of 0.5. So just bear in mind that in all sorts of fields, so including social psychology, Cohen's d of 0.5 is the sort of effect size that psychologists are interested in, or at least to get. Now, so that's on the one hand. The sort of scale of effect that we could be interested in is around about a Cohen's d of 0.5. Okay. Typically, maybe not in your particular case, we'll just say typically as psychologists, and especially for social psychologists. The reason why I say social psychologists is because of this next study, or it's really a presentation that's on the internet by Simmons et al., where what they try to do is use Likert type scales, in other words ratings, and try to get the biggest effect that they could. So this is a deliberate attempt just to set up situations where you would have as huge effect sizes as you could. So they ask people questions like, do you like spicy food, yes or no? To make two groups, those who like spicy food, those who don't like spicy food. Now rate on a 1 to 7 scale how much you like Indian curries. Okay? So, now, the reason obviously they did that was surely the people who say they like spicy food will like Indian curries more than the other group, and surely by a big margin, this was the whole point, to get big effect sizes. The Cohen's d they got was around about 1. And so they repeated this in a number of cases, including how many shoes do you own, men and women, Cohen's d about 1. Now they did get a Cohen's d of more than 1 when they asked how tall are you, men and women. It was only a Cohen's d of about 1.85. In other words, if there's some effect in there that hits you between the eyes that it's so big, you could be talking about a Cohen's d of a bit less than 2. In other words, using Likert or rating scales, which psychologists often use, you don't really expect to get an effect more than a Cohen's d of 1. That's about the most you could expect, okay, for something that was blatantly obvious going to give you a big effect. So the thing I want you to bear in mind here is you're interested in an effect of about 0.5, but the biggest you could expect is about 1. in a range of highly typical cases. I'm not saying it's true in your case, but in a range of in a wide range of research areas. And that's a factor of 2 to 1, ratio 2 to 1. Now, there can't be any law of the universe that the maximum plausible effect size is about twice the value you expect. But I found it such a useful rule of thumb that it is worth considering. And if you consider it, and you think, well, no, that is plausible, there's a very simple way of representing the situation. So this is what we have. We assume a measured effect size roughly the right scale of effect. We assume a rough maximum is about twice that size. And we assume that smaller effects are more likely than bigger ones. Now, there's no reason why these assumptions should be true in a particular case, but let's just say they are true. We can now represent this in a very simple way. This is our model of H1. In other words, our model of the plausibility of different possible population mean differences. Let's put a normal distribution, centre on 0. Now let's say our theory predicts a certain direction, and often a theory does predict a direction. It says people will perform above chance, okay? or you know, the ERP will be bigger in this condition than that condition. That means we can chop off half of the normal because the theory says there's only one direction in which it's plausible. So this is what we so-called half normal. So we have a half normal, which has its mode on 0. We have to fix the standard deviation. That's the one thing we have to fix. Well, that's the scale, that sort of fixes the scale of effect that we're interested in. So we'll let the standard deviation be that estimate we got from the previous study. So in terms of what we were talking about mindful walking, 0.6 we said. Well, there's this previous study that focused on breathing. 0.6 is the right scale of effect. So we'll set the standard deviation here to be 0.6. Now, what is this telling us? Well, you see here that smaller effects are more likely than bigger effects. We've represented in perhaps a simplistic way, but at least a simple way. As we go towards 0 population difference, the effect becomes more and more likely. Smaller effects are more likely than bigger effects. We've scaled with the past study, so we've been scientifically informed, okay, by the sort of thing we expect here. Now the maximum, well, there is no maximum to normal distribution, but let's say we have a rule of thumb or a convention for any distribution we use, that if 5% of the area is left out, then that's effectively a maximum. Well, that's 2 standard deviations out from normal, okay, or half normal. So by using a normal here, or a half normal, we satisfy the assumptions in sort of a simple way. Okay. A rough maximum is twice the scale of the effect we've put in there. Smaller effects more likely than big ones. So you see, modelling H1 is relatively straightforward if you accept these assumptions. And the one I'm going to relax, or say doesn't matter so much, is this twice as big one. And you'll see that was the one that you might, I don't know how it strikes you, but you might have found the one that you're least willing to accept, or is least compelling. Okay. I have to say, that might strike you now if you haven't thought about these things, but having dealt with lots of examples, this 2 to 1 rule just comes up so often as actually being plausible, but it's definitely worth considering as a possibility in the case that you're dealing with. Now, okay, shall we carry on? So to recap, what we're trying to do here is to have a model of H1, what is often called the prior. I don't really like the term prior so much. Prior has often been associated with something subjective. To go back to this. Prior has two meanings. One is your prior odds, and it is something subjective. That's just how strongly you believe in some theory versus the null, and that's completely up to you. But then there's how much you should change your opinion, which is the base factor here. As long as you agree with the statistical assumptions that go into the modelling of the predictions here, then that's something relatively objective. But scientific judgment still comes into it. We need to judge these models are adequate. We need to judge, well, first of all, we need to judge that the model of H0 is an interesting one. In a way, that's some of the criticisms of the people of hypothesis testing. They say that the model of H0 isn't scientifically relevant, you could say, is one criticism. We'll come to that. So you need to judge, no, that is an interesting thing, an interesting model that could be true. You need to judge whether you have a good model of the data. Is it roughly normally distributed? Okay. Taking into account the task subjects were given, past data, how the data look, we come to an expert judgment as this is binomial situation, this is a normal situation, or something else. And we need to judge that this is a good representation of the scientific situation. So judgment comes into every stage here. But what you're doing in this case, the model of H1, which is sometimes called the prior, is you're saying, what does my theory predict? So that's something necessary for getting evidence for the theory. Yes?
Maybe I'm reading the graph wrong, but why is the plausibility under H1 the highest population in 0?
Yeah, no, you're reading absolutely right. So this is the representation I suggested we could often use, this half normal here, which does give a higher plausibility the smaller you get. And that represents the assumption I talked about, that the smaller the effect size, the more plausible it is. Smaller effect sizes are more plausible than bigger ones. And the sort of the simplest, as I say, probably simplistic way of representing that is with a line that just goes higher and higher and higher up to 0. Now that might not actually be your true feeling in the situation, in that you might not think sort of indefinitely small is really more plausible than a bit bigger than that. But it just represents that assumption in a very simple way. We'll look at breaking that assumption later. So see, all these assumptions are for breaking if you think there's a better way of representing the scientific situation. But once you've passed scientific judgment or expert judgment that these models are adequate models of the scientific situation, then you have the guarantee of the axioms of probability that you're getting evidence for your H1 or for your theory as opposed to the null hypothesis. Yes?
So just to come back to your point then, so the intuition though is that, so it is that your model of H1 is saying that 0 is the most plausible value, but still if you get a value of 0, it's going to be better supported by, if you go back to the previous, does that make sense? So
yes, because
I found that really unintuitive when I was first trying to get my head around this, but it's because the top one is still more plausible if you get a value of 0 than the bottom one.
Exactly. This theory, the null hypothesis, is saying there's only one possible value, which is 0, whereas this H1 is saying it could be anything from 0 up to some effective maximum exactly. So when you do get a value of 0, that will be better predicted by H0 than it will be by H1. That's right. But by making 0 very plausible, or the most plausible value in H1, it makes it, and to go back to your point, it makes it harder to distinguish H1 from H0, you see. And that's, in fact, why I like it. Because then if you do get a distinction between H1 and H0, you've done it despite your assumptions. So by using a somewhat simplistic way of smaller values are more likely than bigger values, we've sort of stacked things a little bit against us, finding discrimination in typical cases, and that's how it should be. So just to go back to terminology, one use of the term prior in the literature is this model of H1. In other words, one meaning of prior is specifying fully what your theory predicts, and the other meaning of prior is your prior odds. You see the two different states of affairs. And I think your prior odds here can often be regarded as completely subjective, non-problematically. But what I report in my papers is the Bayes factor. I don't say how probable I find the theory. That's up to you. I might find subliminal perception really rather plausible. You don't. Absolutely fine. Our inference is going to depend not on that, but the Bayes factor, typically. So that's why I prefer not to use the term prior, but to say what does your theory predict with the model of H1. so let's go back to the example where, as I say, I took it from an actual intervention study by Kate Kavanagh and people at the University of Sussex, where a 2-week intervention increased mindfulness by a certain amount. Okay, so now we decided if in the intervention we thought in a new study, the walking study, we would expect the same sort of effect size by and large, at least the right scale, we could use this half normal to model what we predict. But I want to illustrate that's not the only way we could go. Let's say we have the same original study, except in the follow-up what we do is, okay, this study they practiced for 2 weeks. Could we make it even shorter and still get effects? Because, you know, shorter interventions are good, more people are likely to stick to them, and so on. Can we still get some change in mindfulness if we use 1 week instead of 2 weeks? Well, now that changes the situation a little bit, because if 1 week has an effect, I think it's very plausible to say it can't be more than the 2-week effect. Okay? So the 2-week effect provides a sort of rough maximum to what we could expect. So this is a situation where when we point to another study, it's not just the right scale of effect. It's something that we think we probably couldn't exceed. It's a plausible maximum. Well, one way I've operated in the past, and Bayesians have since Jeffreys, is to think, well, the population effect could be anything from 0 to that maximum. And in the absence of any other information, we'll assume that all these possible population effects are equally likely just because that's simple. Okay. Well then, what these assumptions will give us is a uniform, it's called a uniform distribution, or a rectangular distribution, where the plausibility of different population effect sizes is the same for all the values we regard as possible, which is anything from 0 up to that rough maximum. So you could use a uniform. I used to do that rather more just because I found in my papers when I'm talking about how did I model H1, I mean, why am I using those distributions? If I specified a maximum, to say I did a uniform from 0 to that maximum just seems simple. But, okay, people will understand that, will understand why I'm doing it. Nonetheless, the considerations I mentioned earlier about smaller effects being more likely than bigger effects lead me these days to prefer the half normal still, where I would set the standard deviation equal to half the maximum value. Because remember, twice the standard deviation is sort of the effective maximum. But just alert you to that, because Bayesians, as I say, from Jeffreys onwards, 1939, have used uniforms. I hope you understand the sort of the logic of that, but I still prefer the half normal. Now there's another distribution you'll see around, so I want you to understand that as well, because it's pushed by almost all the other Bayes factor people, who aren't me, in other words. And that's the Cauchy distribution. So now the Cauchy is this thick one here, and the normal is that dashed one. And you can see the Cauchy is a bit like the normal in the sense it's sort of this bell-shaped distribution. But how it differs is it has very thick tails. Now, how that changes things is, remember with the normal, I said if the standard deviation is some value, and the maximum is about twice that, in terms of 5% of the area. Because of these thick tails here, the scale factor, which is the equivalent of the standard deviation for Cauchy, is some value. The maximum is about 7 times that. And that's the sort of the, what I take to be the crucial difference in terms of understanding or thinking about which of these distributions would you apply in a particular scientific context. If you have a certain expected scale of effect, is the maximum more like twice that effect, or more like 7, 8, 9, 10, it all bunches together a bit? I'll give you an example of that so we can think about that. So to calculate the Bayes factor, we must decide basically, what does our theory predict? I mean, in any measure of evidence, I think, if you want to know whether you have evidence for your theory, you need to know what your theory predicts. That's sort of self-evident, and that is why the Bayes factor asks for it. And so you have these choices. With the Cauchy, all of these, by the way, uniform, normal, Cauchy, were used by Jeffreys in his 1939 book. So all of these have been there from the beginning as possibilities. And of the Bayes factor calculators you'll find out there, well, there's now on the web a version of mine that does all of these, and lots of versions that do the Cauchy, particularly coming from Jeff Rauder or Richard Moray. So one thing I want to talk about is, well, when would you use one or the other, and what difference does it make? So this is mine one. If you sort of Google my name, you come up with it. This one will do uniform or normal distributions, R for full. You can center the normal anywhere you please, and they'll do raw or standardized effect sizes. And then about a month or so ago, I was emailed by a chap from India, Singh, who had programmed up my calculator in something other than Flash, which actually was extremely useful for me because I was just starting to get emails from people saying my calculator wouldn't run on their computer anymore. And I looked into it and found out it was because browsers had started blocking Flash programs, and it was sort of quite straightforward to reset. I say on my website how you can click on something that enables Flash again, but it's all a bit of a nuisance. So this is not Flash, and so an easy way around it would be to, if you wanted an online program that you just deal with, you could use this one. This doesn't depend on Flash at all. The other thing he did, which was extremely useful, was to put in the calculator modelling H1 with a T distribution, which I've also recommended. And if you set the degrees of freedom of that T to 1, it is a Cauchy. So you can do Cauchys with this as well. And you can center it anywhere you want, and you can use raw effect sizes as well as standardized, a point I'll be coming to. So I link to this on my webpage, yeah.
So is it the case that you can use either raw or standardized effect sizes in either the normal or the Cauchy?
Yes.
Okay.
To do that with my calculator, what you do is convert to Pearson's R as your standardized effect size, and then take a Fisher Z of that. And I mentioned that in my website. And then, if you're looking for Bayes factor calculators on the web, you've got Jeff Rauder's, straight Richard Moray's on Rauder's site. And that models H1 with a Cauchy, just standardized effect sizes and just centered on 0. So that, so far what I hope I've done is to set up the problem, put in a bit of context of other Bayesians you'll come across, and indeed to non-Bayesians, who try and solve the problem of getting evidence for H0 by using estimation procedures. So the problem is, to estimate, you need to specify a null region, and specifying the limit of that region, or the minimal interesting effect size, is what I found difficult in a non-arbitrary way. With the Bayes factor, you still have to specify something, but what I found a lot easier is to specify the sort of effect size that I'm expecting. And I don't reach deep in my soul to come up with that. I point to that paper or that meta-analysis and say, that's the effect there. That's why I put it in my calculators, because that study got it, that meta-analysis got it. And that I found non-problematic, or specifying a rough maximum, I found non-problematic. Even if it's just a rough estimate, I'm saying, I'm using that number because that's what that paper got, and I point to it. Whereas specifying a minimal interesting effect size, I haven't found it possible to point to a paper and say, I'm using that number there in that paper, you see. Right, but now we have this issue of saying, what does our theory predict, which is what we haven't quite been used to saying. I hope I've illustrated. Maybe it's not so difficult, but you still have choices, right? Is it Cauchy, uniform, normal? what do I set things to? So I want to go through some principles, which I said before, I hope to work into a consensus statement that I'll get as many Bayes factor people to sign up to as possible. So there's sort of some agreement about the principles by which one uses Bayes factors. Right, so we'll go back to the study with focusing on breathing. I've made up some numbers here. It's sort of just significant in the original study. So you do walking meditation, everything the same. How do we model H1? Well, the rough scale of effect we predict is the same as the previous study. You know, why should focusing on walking be any different from focusing on breathing? And then I said you could use a half normal if you thought a plausible maximum is about twice that effect. Now, I didn't pick these numbers out of the blue. I've deliberately referred to sort of real data, as it were, to constrain myself. And on this scale, I looked up, it's undergraduates, sort of unselected undergraduates, unselected in the sense they haven't been selected for being particularly mindful or unmindful, score about 3 on the FFMQ, thereabouts. And if you take experienced Buddhist meditators who've been doing it for 10 years and locked up tens of thousands of hours of mindfulness, they score about 4 on this scale, as a matter of fact. Okay? So, sort of, you know, I'm not making this up in order to force a fit. So now, if we were using a half normal, we would say twice this is the rough maximum. So twice that is 1.2. So that would be going from 3 to about 4-ish. Now that seems to be reasonable as a maximum, especially if 10 years of Buddhist meditation lands you at 4. 2 weeks is unlikely to beat that. Of course, there's demand characteristics and stuff in the study. So I reckon that's quite plausible. Whereas if we used a Cauchy, the maximum would be change would be 7 times that, 4.2 units. So you'd go from 3 to 7, which is off the scale. So in this case, it strikes me that the normal is the actually rather plausible representation of our scientific knowledge in terms of modelling what's going on here. So half normal would be more appropriate than the half Cauchy. So I can set up a half normal. We'll have 0 as the mode, in other words, what was the mean of the normal, and 0.6 as the standard deviation, and a half Cauchy, which we can set up with the same units. And if you wanted to check this, you can use the Singh calculator I referred to, which you can get to by Googling my name, going to my Bayes site, and then I link to the Singh calculator. Well, let's say the new study, the effect is a bit smaller than the original one, as I said, will often be the case. It's just significant. If we do the Bayes factor with a half normal, it's 3.5. Now, do you remember what 3.5 means? It's just above the cutoff that Jeffries had said, and journals actually tend to use for that reason. And this cutoff of 3, you see that's pretty close to 3, and a T of 2 is pretty close to 5%, it's just less than 5%. So we remember this correspondence I said that if you get an effect that's roughly what you expect, but you're going to get a Bayes factor around 3 for something that's just significant. So that illustrates that correspondence. Notice something else I've done here is I've notated my Bayes factor to say what is the model I'm using. One problem I see, I'm delighted when I pick up a paper and I see Bayes factors in the results section. More and more people are doing that, but often what I see is just B equals something and no discussion of what was the model of H1. And that's sort of meaningless because what a Bayes factor does is it compares one model with another model. And unless you say what the models are, it doesn't mean anything, right? So always say how you modelled H1 when you use a Bayes factor. And always justify it as well. Now, I've put here the half Cauchy. And you notice there's a bit of a difference. But actually, really, it's pretty similar. one message I want you to take home is, of course, there is a bit of a difference, and as I've illustrated here, it could span some conventional boundary and to give you analytic flexibility. You can always b-hack with a base factor as much as you can p-hack. But the difference here isn't great. In other words, this assumption about what the maximum is doesn't play that much of a role. I mean, to the extent it does play a role, which it does, in this case I think it's clear you go with half normal rather than half Cauchy. But let me look at a plot here of half normal versus half Cauchy. This is the line of identity, and we're going, this is 0.01, which is one conventional cutoff, 1/10 you could have as evidence for H0, sorry, 1/100th, 1/10th, 1/3, or 3, 10, 100, sort of some conventional cutoffs. And you see the points remain over that full range, just a little bit below the line of identity. In other words, that illustrates half normal, half Cauchy doesn't really matter that much. Though the Cauchy will tend to prefer, just by a slight amount, H0 versus H1. That's what it means by the points being just below the line. But you can see for any given cutoff, like a third here, see how close the half Cauchy and the half normal are. That was a little bit of a surprise to me, I have to say, but in a way I'm relieved, because it means when people use a Cauchy versus a normal in situations where I think the normal might be more appropriate, it doesn't actually matter. Okay. And that's not to say your model of H1 doesn't matter. I just want to illustrate the case where it does matter. It just so happens, as long as you've got the same scale factor for the raw effect size in that case, for standardized effect size, it doesn't matter that much whether you use a Cauchy or a normal. But other aspects of the model do matter. So let's say what I've done here is contrasted the case. We might have two different initial studies. One initial study, you get a very small effect of mindfulness, 0.2 units. Okay. So from 3 to 3.2. Or the initial study might have had a really big effect in terms of the scale, 1.5 units. And the difference is like looking for the cat or looking for the elephant. Okay. And then we get, we do our study with walking meditation. It's reasonably small effect. It's non-significant. What does that non-significance mean? Well, we get an effect, a rather small effect, and in this case, because the initial study was quite small, the signal we're looking for is really quite small. Now, in this case, where the initial study was big, the signal we're looking for could be anything from small to enormous. And that should make a difference to whether we think we have good evidence for the null hypothesis. Whether we're looking for something that could be big, or we're looking for something that is necessarily small. Now, one thing I want to point out here is the effect on this model still could be very small. But let me give you an analogy from physics that I don't know if you sort of follow in general the Large Hadron Collider and the particles they're looking for. And I found the Higgs, which is great, and something else they're looking for is particles predicted by supersymmetry, which is a model that could replace the standard model that they have, and it predicts new particles. And in terms of the masses of those particles, they've already looked in a region of possible masses, but there's another region there which they haven't been able to look at yet, haven't been able to get to yet. So they've looked in this region, and they haven't found those particles. So they haven't falsified the theory, because there's still this region they could look in. But at least sort of my reading of the popular science and nature and things, their confidence in supersymmetry has gone down, because the particles could have been this size, and they haven't seen particles of that size. So here, the fact that the particle could have been, not the particle, the effect size could have been this big, but we didn't observe it this big, counts against the theory, even though it could have been this small. Do you see what I mean? So it's not that we falsified the theory, but should it not count against the theory that we've observed something only very small and it could have been huge? Does that make sense to people? So, in fact, if you put the numbers in a base factor calculator with a half normal, h stands for half normal, we've set the mean of that normal before we cut off half to 0. Standard deviation is 0.2 here, because that was the original study, very small. 1.5 here, huge in the original study. Here the base factor narrows down at 1. In other words, because what we're looking for is very small compared to the standard error, the evidence is just insensitive. It doesn't tell us anything one way or the other. Here, because what we're looking for could have been huge, even though it could have been small, the fact that it could have been huge, and we didn't observe huge, we observed something quite close to 0, that actually does count against the theory. In fact, it's less than this conventional threshold of a third, which is pretty much equivalent to the sort of evidence we would get with 5% in terms of establishing there isn't.
What would you do? So often there's more than one study, and often they're like that. So one finds a really tiny effect, and one finds a really big effect. So in terms of calculating your own estimate of what might happen, how would you weigh those two things up?
Yeah, so the question is, we have a range of possible effect sizes from past studies.
Yeah.
What is your scientific... So the ultimate question is, what is your scientific judgment of the range of effect sizes I could expect in this study? So what you could do is take the range of previous effect sizes to fix your range, or you might take a meta-analytic mean of them, and do the half normal on that meta-analytic mean, which would probably be what I tend to do. So, I mean, a meta-analysis, if you have a whole range of studies bearing on the issue, that would be better than just basing it on a single study, because then you're being better scientifically informed. So, in fact, it's a good thing that there's past previous studies. But you might want to consider, there's always a trade-off, by the way, between simple and informed. I said what you want to do is be simple and informed. So you might decide, to keep it simple, I just take the meta-analytic mean and use that, much the way I have. Or you could be more informed and say that my study is more like this set of studies.
Right.
So I'm going to use that particular set with all their sort of details, which matches mine more. And in the end, that's a scientific judgment. But one thing about when you do the base factor is you should always make your reasons explicit, so that people can judge for themselves whether those are reasons they wish to dispute. Yes.
So along those lines, would you say you should also, I mean, you can acknowledge that you're choosing some model which is more conservative or less conservative.
Yes.
So, you know, we found this evidence for H0, but bearing in mind this is a relatively conservative. Do you see what I mean? It could be something you would discuss almost in the discussion section or something.
That's an excellent point, yes. So where there are different legitimate ways you could model H1, you can and should do the different, use those different models, and then discuss it in the discussion. I mean, in an ideal world, they lead to the same qualitative answer, like B greater than 3 or less than a third in each case, or maybe in most cases. I do have one paper where you put in different assumptions, and we got qualitatively different answers, and I said the matter is just left open because of that. If you could run more subjects, get more data, until all the models agreed, that would be nice. One's not always in a position to do that. I'll come back to that issue, actually, that very issue. So the overriding principle is the models of H1 and H0 depend only on scientific judgments of their adequacy, in terms of the base factor you're getting being legitimate, as it were, or appropriate. So in other words, there's no statistician who can tell you you should be doing this. It's not a statistical matter, ultimately. It's a scientific matter of whether this is a good model of the scientific situation. And given that you judge that the models are adequate models, good approximations to one's scientific judgment of what's going on, you have the guarantee of the axioms of probability that you are getting the evidence for one theory versus another. And so that is the overriding principle that trumps everything else that I'm going to say. So given that, in the end, it's a matter of scientific judgment, nonetheless, it's useful to have a set of principles, or sort of defaults that you consider, bearing in mind it's always open to you to reject them in any given case. So I'll go through the principles that I find apply in 99% of cases for your consideration, because I think they'll apply to the cases that you use as well. So smaller effect sizes are more likely than larger ones, so use a distribution with an over 0. Use other estimates to set scale of effect. Be scientifically informed, in other words. If a plausible maximum is about twice the scale, use a normal. If closer to 7 to 10 times, use a Cauchy. But as I say, fortunately, this particular principle makes little practical difference. But nonetheless, to the extent it makes a difference, you have a reason for choosing one rather than the other. And if the theory predicts a direction, use a half normal, a half Cauchy to represent the direction. But if either direction, in fact in either direction, be perfectly fine by the theory, then you use a normal or a Cauchy centered on 0. So those are the principles I've considered so far, and also represent not just what I've done in my papers, but what is actually typically done in papers that use Bayes factors, that draw on other Bayes factors calculators as well. But, of course, we can, you're not obliged to use any of those principles, because, as I say, the overriding principle is that it's a good model of the scientific situation in your expert judgment. Remembering your expert judgment will be subject to the criticism of your and oversight of your colleagues. So the question I said before was, we brought up before, was smaller effect sizes always more likely than bigger ones? I mean, there may be a case where we say some parameter, it's going to be far from 0. I know it is. There's no question of smaller being bigger than smaller being more plausible than bigger. For example, there could be some learning situation where you know you're going to train people a lot, and you know they're going to perform reasonably well, and there's no way that they will get, a D prime of 0.1 or 0.2 or 0.3 or percent correct or 55%. It's going to be 75%, 80% correct. Okay? Maybe 65%.